3.1 we're going to do in two parts. First part, in this chapter we will study exponential and logarithmic functions. These are non-algebraic functions. They are examples of transcendental functions. An exponential function just means that there's an exponent within the function, where a is greater than 0 and not equal to 1, because if it was a 1, anything to the 1 to any power is always just going to be 1. And x just has to be a real number. So it can be positive, it can be negative, it can be absolutely anything. When we do these kind of examples, use your calculator and come up to 3 decimal places. Okay, so 4 to the 4th. Use your calculator. 4 exponent 4. Exponent is that little caret key. So we get 256. 4 to the 1/2. Now be careful with this, because if you go 1 divided by 2, it's not going to work. Order of operation says the calculator is going to do 4 to 1 and then take the answer and divide by 2. Alright, so you need to make sure that if you're doing fractional exponents and stuff, that you're using appropriate parentheses. So 4 to the 1/2 is the same as the square root of 4, so we get 2. 2 to the negative 4.1. So 0.058, make sure we're rounding appropriate. Again, 3 decimal places. 2 to the negative pi. Pi is the second caret key right above that. Again, 3 decimal places is fine, and round appropriately. And then 3 to the 5/7. So 2.192. So let's just, can you use your calculator? Do you understand how to use parentheses appropriately? When we look at the graphs of these exponential functions, we're going to sketch these using first coordinate points. So with your calculator, you can put in 2 to the negative 2. Because that's just 2 to the negative 2. Negative exponents, remember, that means to reciprocate, so that's really 1 over 2 squared, so 1 to the 4th. And then if you have your g equation, so 4 to the negative 2 is 1 over 4 squared, which is 1/16. And you can continue filling in this t-table. So if you just pause for the video for a minute, fill in this t-table according to what you have, and then come back and I'll have it filled in. Alright, those are the numbers that you should have got when you did your t-tables, and now it's a matter of looking at the pictures. So when my f of x equation, at negative 2 I had 1/4, 1/2, 1, 2, 4, and then we're off the charts up here at 8. Okay. And that's our f of x equation. G of x had 1/16, 1/4, 1, 4, and then way up here at 64. And that was our g equation. So notice it increases, the 4 base increases a lot quicker than the 2 base. So again, pause your video, fill in the t-table according to these values. So if I have 2 to the negative negative 3, that's really 2/3. So I get 8. All right. When we go to sketch them, we are at 8. The other one's at, let's go, -2 is 4, -1 is 2, 0, 1, 1/2. Okay, so notice that one decreases with the negative exponent. And then notice this one decreases just quicker. Your G equation and your F equation. So all that is showing you is how our graphs can increase and decrease based on whether we have negative x's and positive x's. And that's what this next page is talking about. Typical exponential functions have one y-intercept and one horizontal asymptote, generally the x-axis. If the graph is a to the x and x is positive, that's really the difference between these two scenarios. X is positive and x is negative, because in both situations the a is greater than 1. Notice the domain is the same, the range is the same, the intercept is the same. What changes is the increasing and decreasing, and what changes is where does it approach. As the values get closer to 0, the x values get into infinity. As it approaches from the negative, it approaches the positive. So on this one where x is positive, it increases. Where it is negative x, it decreases. Keeping in mind that the x-axis is the horizontal asymptote in both situations. And as x approaches infinity, the y values approach 0. And that's what that says. As x approaches negative infinity, see how we're getting closer out here to negative infinity? The y values approach 0. And again, that's just what that says. And it is continuous, it doesn't stop, it doesn't end. It keeps going on forever. Alright, f of x equals 4 to the x. We're going to do some movements with it, just like we've done with all of our graphs. If the 1 is with the x, that means we're going to have x movement, that we are going to be going 1 to the left because we're going to do opposite. We're going to do 3 down because that's our k. Here the negative function means it's going to reflect over the x-axis, and a negative x value means we are reflecting over the y-axis. So in general, when it comes to our transformations, they're very similar to what we've been already working with all of our h's and k's, with all of our different polynomials. So what we have here is a general form, y equals a, x minus h, plus k. H moves us left and right, k moves us up and down, and once we start putting negatives with those things, we start reflecting over x's and y's. One thing we do need to be careful of, for example, when we start changing our transformations, we are also going to be changing our y-intercepts with each transformation. It also changes, like up here, if I change my movement up and down, it changes the asymptote. The asymptote is actually going to change to the k value. So in this case, the asymptote is going to be -3. Y equals -3. So kind of a unique property to our logs with that. But the movements, reflections, all those are the same as h and k's. Just know that that changes our asymptotes and our y-intercepts once we start also doing transformations. All right, page 5. We have what's called the natural base of E. E is called the natural base. It is this value, 2.71828. You do have an E on your calculator down here above the ln, so second ln, and you just put it to 1, e to the first power. That's what E represents, 2.71828, blah, 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 continuous forever. So the natural exponential function means that E is being used in my exponent representation. The domain is all reals, the range can only be from 0, and the intercept is from 0 to 1. If we look at the graph, y equals e to the 1, you will see that picture. Oops, let's do it on a normal window. There, oops, y equals, oh, how about e to the x is what we want. There we go. Y equals e to the x. It's very, very similar to the functions that we just had. It has a y-intercept. It approaches our x-axis as an asymptote. The way that this number came about, it came about from this formula. So if I put 10 in, then 100, and then 1,000, and 10,000, 100,000, a million, you get these numbers: 2.59, 2.70, 2.77, 2.718, 2.71826. Let's go back here a little bit, 1.5, 2.71828. And notice as my x's approach infinity, because they're getting bigger and bigger and bigger and bigger and bigger, my y values, also known as f of x, is approaching the value of e, of which we did up here. This is nothing more than a proof of why this number is the way it is. Beyond that, we really don't need to do anything more with that. You just need to understand that e is our natural base number. E is an actual number, just like pi is a number, even though we're using a symbol. E has its own value on the calculator. So when you're asked to evaluate for E, just use your calculator. E to the -2. And give me 3 place values. 1, 3, 5. Make sure you round appropriately. E to the -1. 0.368. E to the 1. 2.718. E to the 2. 7.389. So just use your calculator. We really don't need to do the proof, anything beyond what we've already done. Know that it looks like our other exponential functions and that it is an actual value, but we're going to use our calculator for most of it. So that's going to be 3.1 part 1.